Okay, we're going to start talking about a new type of function, which is called our exponential function. So we've looked before at functions that have exponents. So for example, x squared functions, x cubed functions, radical functions such as x to the 1/2 or x to the 1/3. Notice in all of those functions that my base, my thing that's being raised to an exponent, is a variable, while my actual exponent is a number. The difference that we're going to, or the thing that we're going to switch to now with exponential functions, is our base, our thing that's being raised to a power, is going to be a number, while our exponent is going to be a variable. So, such as here, x squared versus 2x. We're going to be looking at functions like 2x. So let's look at some properties of exponential functions. Exponential functions are always going to be in the form of a times b to the x. So notice in this first example that I gave you, my a would be 1 because I have 1 times 2, which is my b to the x. A cannot be 0. B has to be greater than 0 and B cannot be 1. We are going to discuss these restrictions in class and talk about why they exist. So if you want to already start kind of putting yourself in that mindset, start thinking about why might A not be able to be 0? Why might B have to be greater than 0? And why might B not be able to be 1? When we look at graphs of exponential functions, there's two different graphs we're going to get. We're going to get growth functions and decay functions. Growth functions are going to have these characteristics here. My base is going to have to be greater than 1. When my base is greater than 1, as I just referenced, it'll be a growth function or an increasing function. Our x-axis is going to be a horizontal asymptote. Remember, to be an asymptote, it means I get super, super, super close, but I never actually touch it. So if my x-axis is the horizontal asymptote, that means I have a horizontal asymptote at y equals 0, because on the x-axis y is 0. Sorry, my 0 is kind of smushy. But I'm going to get really close to having a y value of 0, but I will never actually touch it. So if you think about in terms of domain, I'm going to have that parenthesis at 0 as opposed to that bracket, if you think about what we talked about in a previous unit. When I look at my y-intercept therefore is not going to exist since I can't actually touch the y. Oh, excuse me, that's the x-intercept. My y-intercept is always going to be 1. So when x is 0, y is 1. My x-intercept will not exist because I remember, again, I have that horizontal asymptote there. My domain, as I just referenced, is going to go from negative infinity up to infinity. And my range, because I can't actually get down to y equals 0, my range is going to start at y equals 0 and go up to infinity. My graph, and I'm going to move over to the side a little bit here, so I'm going to kind of have to bounce back and forth. My graph is going to look something like this. Again, here's 1. And as I continue, this will continue to get closer and closer again to that x-axis with never actually touching it because of that asymptote. So here's my x-axis, here's my y-axis. That is an exponential growth function. Decay function is very similar, except for now my b value, my base, is going to be between 0 and 1. My function is now going to be decreasing or decay. I'm still going to have that x-axis as a horizontal asymptote. My y-intercept is still going to be y equals 1. My x-intercept still will not exist. My domain is still going to go from negative infinity to infinity. And my range is still going to go from 0 up to infinity. The difference is now when I look at my graph of my decay function, I'm going to start with high values, and they are going to get low and approach towards that horizontal asymptote, whereas with the growth function, I started down low and I got exponentially higher and higher. So the only difference that I need to touch on with the graphs is, of course, all of our sketching rules or translating rules that we learned before will still apply to my exponential functions. So as my graphs get shifted, keep in mind that these characteristics are for f of x equals b to the x. So as I apply different translation or shifting rules, I may have some different y-intercepts, x-intercepts, asymptotes, etc., etc. So looking at just a couple of these where I want to sketch some graphs. giving myself an axis here. When I have y equals 4 to the x, well, this is the same thing as taking my b and making a larger b. So as my b gets larger, I'm going to vertically stretch. So I'm going to go ahead and say that it's going to look very similar to what I had before. I do know it's growth because 4 is greater than 1. On number 2, y equals 4x minus 2. So now I'm going to take that same function I just drew in example 1, and because I'm subtracting on the inside of my function, that tells me to go right 2. So when I go right 2, that also means that my y-intercept is going to shift right 2. So I'll have the 1 here, and there's my new function. So it looks exactly the same, just shifted right 2. On number 3, I'm adding to the outside. Remember, if I add to the outside, that shifts my function up. So I'll go up 1, 2, 3. Now when I move up 3, I will have a y-intercept instead of at 1 at 4. And instead of having a horizontal axis on my x, a horizontal asymptote on my x-axis, I'm going to have a horizontal asymptote moved up 3 as well. So my horizontal asymptote, moving that up 3, is going to be right here. And then I draw my function in, and again it looks the same, just shifted. Finally, looking at 4, 5, and 6, if I want to put a negative out front, remember that's going to shift me over the x-axis. So instead of having my y-intercept at 1, my y-intercept will be at -1. I still have that horizontal asymptote, and I still now extend, instead of towards infinity, towards negative infinity. Remember, putting a negative inside of my function, such as in example 5, is going to reflect me over the y-axis. Therefore, my exponential growth function is all of a sudden going to look like an exponential decay function. And lastly, when I add 5 to the inside of the function, that's going to have me go left 5. Very similar to number 2 I graphed wrong, so I'll go back and fix that. I apologize. So I go left 5, 1, 2, 3, 4, 5. And I'm going to go ahead and then shift my y-intercept over 5, and again keep that same shape. And I'm going to fix number 2 before I touch on the last piece of information for this video. On number 2, I should have went right 2, so I should have looked something more like this. So I apologize for that. Finally, the last thing I have to touch on before the end of this video is what we call the natural exponential function. We will look at some more at this in class. Natural exponential function is defined by e to the x. E is very similar to pi in the aspect that it is a defined value. E is approximately 2.78. So this gives me 2.78 raised to the x. Therefore, when I ask myself what two functions should e to the x fall in between, e to the x is going to fall in between 2 to the x and 3 to the x. But it is just another exponential function, and it is referred to as a natural exponential function because it does occur so often that we have given it an actual definition. Again, it's very similar to pi.